Basic GPIO on ESP32 with R1-bit. Let's go through the core hardware features you'll run into in most ESP32 projects with R1-bit. Out. Digital output. The out command lets you control any free GPIO directly from a script, as long as the pin isn't already taken by the system or another peripheral. Let's assign a pin as an output and write a simple script that toggles it every 500 milliseconds. As you can see in the video, the LED turns on and off every half second. DAC, analog output. The DAC command is for when you need more than just on or off, when you need to set a specific voltage level on the output. Let's assign a pin with DAC support. One important thing to note here: the original ESP32 had a true 8-bit DAC. Newer chips, S3, C3, P4, don't have a classic DAC. Instead, they use a sigma delta modulator. It generates high-frequency pulses whose average value produces the desired voltage level. For most use cases, controlling LED brightness or powering a low-current load, this works perfectly fine. But if you need a clean analog signal, you'll need an external RC filter on the output. Resolution is 8 bits, 256 steps from 0 to 3.3 volts. In the video, if you gradually change the value in a loop, you get a smooth fade-in and fade-out effect. In, digital input. The in command reads the state of a GPIO and returns 0 or 1. Let's assign a convenient pin as an input. 2 pull modes are supported. Pull down. An internal resistor pulls the pin to ground. The button connects the input to 3.3 volts, so we read 1 when pressed. Pull up. The pin is pulled to the supply voltage. The button shorts the input to ground, so we read 0 when pressed. These mode to use depends on how your button is wired. In this example, we'll display on when the button is pressed and off when it's released. Touch, capacitive touch input. Now let's look at another interesting digital input mode, the capacitive sensor. It's supported on ESP32 S3 and P4 boards, and, unlike a regular button, it requires no mechanical contact at all. The principle is straightforward. The touch pin is connected to a metal electrode, a piece of foil, a copper wire, or a pad on the board. When a finger gets close to or touches the electrode, the capacitance of the circuit changes, and the ESP32 detects it. The key advantage is that you don't need to touch the metal directly. The electrode can be hidden inside an enclosure with plastic or glass up to 2 or 3 millimeters thick on the outside. A touch on the surface will still register. This opens up some interesting design possibilities. Touch zones built right into the device enclosure with no visible buttons at all. The input returns 1 when a touch is detected and 0 when there's none. In practice, it's a button with no moving parts, no contact bounce, and no holes in the enclosure. Let's see how simple and responsive this is in real use. ADC, analog input. The ADC command measures the voltage on the input and returns a number from 0 to 4095. Converting to volts is a simple formula. Multiply by 3.3 and divide by 4096. Let's assign a pin with ADC support. We read the value and display the calculated voltage on the screen. Connect a potentiometer to the input. Turning it changes the voltage, and you can watch the value update in real time. PWM, pulse width modulation. PWM is one of the most versatile tools when working with hardware. It allows you to generate pulses with any frequency and duty cycle on any available GPIO pin. Let's assign 2 PWM channels. For a visual demonstration, we'll output a 10 Hz signal with a 20% duty cycle to an LED, and also show how to control a servo motor using PWM. In the video, we see a 10 Hz frequency on an LED using PWM. But LEDs are just the beginning. We also see how to control a servo using PWM. PWM is also useful in motors, sensors with a PWM interface, and any external peripherals that require a pulsed control signal.